Why magnets defy classical physics and what that means for reality. Pick up any magnet near you right now, a refrigerator magnet, a magnetic clip, anything with a visible pull, and hold it 1 centimeter from a metal surface without letting it touch. Feel that. There is a force pressing against your fingertips from across empty space, no contact, no wire, no mechanism you can point to. That sensation, that resistance in the gap, is the thing this entire explanation is about, and you have already felt it in your own body before a single mechanism has been named. The force is real. The explanation for it is one of the most unsettling results in all of physical science, and it begins with a theorem almost nobody outside of physics has heard of. In 1911, and then more completely in 1919, the Dutch physicist Hendrik van Leeuwen proved mathematically that if the universe obeyed classical mechanics, the kind Isaac Newton wrote down and James Clerk Maxwell extended with his equations of electromagnetism, every material in existence would have precisely zero magnetism. Not weak magnetism, not reduced magnetism, zero. The Bohr-van Leeuwen theorem, as it is now called, is not a controversial or contested result. It follows directly and rigorously from the equations classical physics itself provides. The theorem says that at thermal equilibrium under classical rules, the net magnetization of any material is identically zero. The magnet you are holding exists in a universe the theorem says cannot produce it. That is not a paradox. It is a signal. It is the universe telling you that classical physics is incomplete, and the thing that completes it is quantum mechanics, a framework whose rules are not intuitive extensions of everyday experience, but genuinely different principles about how matter and energy behave at small scales. Everything that follows is quantum mechanics expressing itself at the scale of your fingers. Start with the smallest relevant structure, the electron. Every electron in every atom in the magnet you are holding possesses a property called spin. Spin is not rotation. The word is historical, chosen in the 1920s when physicists first discovered the property and guessed, incorrectly, that they were observing a tiny charged sphere turning on its axis. Subsequent measurement ruled out that picture decisively. An electron cannot be rotating in the classical sense because the surface of any plausible electron-sized sphere would need to move faster than light to produce the measured magnetic moment, which is physically impossible. Spin is instead a purely intrinsic quantum mechanical property with no classical counterpart whatsoever. Your gut instinct to picture something spinning should be noted and then set aside entirely. What spin actually is, at the level of what the universe is doing, remains one of the genuinely open interpretive questions in physics. What spin does is well established. It gives each electron a tiny magnetic moment, a vector quantity meaning it has both a magnitude and a direction, measured in units called Bohr magnetons. The magnitude of a single electron's magnetic moment is 9.274 times 10 to the negative 24th joules per Tesla. That is a fantastically small number, but there are fantastically many electrons in any macroscopic object, and the question of whether they add together or cancel is the entire question of whether a material is magnetic. The answer is determined by what spin does under quantum rules. Spin can point in only two orientations relative to any measurement axis. Physicists call these spin up and spin down. There is no intermediate state, no diagonal, no continuum of angles. This two-state discreteness is itself a quantum mechanical fact with no classical explanation, and it is what drives everything that follows. Now consider why most materials are not magnetic at all. Your hand is not magnetic. The copper wire in the walls around you is not magnetic. Aluminum, gold, glass, water, none of them stick to anything. The reason is a principle articulated by Wolfgang Pauli in 1925, now called the Pauli exclusion principle. The principle states that no two electrons in the same quantum system can share all the same quantum numbers simultaneously. Because spin provides one of those quantum numbers, and because spin takes only two values, electrons in atomic orbitals pair up naturally. One spin up, one spin down, occupying the same spatial orbital together. When they do, their magnetic moments point in exactly opposite directions and cancel with arithmetic precision. A paired orbital contributes zero net magnetic moment to the atom. In most atoms, in most materials, most electrons are paired this way. The pairing is energetically favorable in a wide class of situations, so nature defaults to it, and the default result is non-magnetic matter. The iron in your blood is bound in hemoglobin in a configuration that leaves some unpaired electron spins, which is why blood is slightly paramagnetic and will weakly orient itself in an MRI machine's field, though not nearly strongly enough to produce any force you would feel. The iron in the magnet you held a moment ago is in an entirely different electronic environment, and that difference is the whole story. Elemental iron, cobalt, and nickel are ferromagnetic, meaning they can sustain a spontaneous macroscopic magnetization without any external field being applied. The reason starts with their electronic structure. In transition metals like iron, the 3D orbital shell is only partially filled. Iron has 4 unpaired 3D electrons per atom, cobalt has 3, nickel has 2. These unpaired electrons are not paired, and so their individual magnetic moments are not internally cancelled. But unpaired electrons alone do not create a permanent magnet. Paramagnetic materials also have unpaired electrons, and they are not permanently magnetic. The critical additional ingredient is called the exchange interaction, and it is the central mechanism this explanation needs to make precise. The exchange interaction is a quantum mechanical effect that arises from the combination of the Pauli exclusion principle and the electrostatic repulsion between electrons. It has no classical analog. Here is the logic. 2 electrons near neighboring atoms will, if their spins are antiparallel, be allowed by the Pauli principle to occupy overlapping regions of space, because they are in different spin states and therefore distinguishable at the quantum level. But if they are allowed to overlap spatially, they are closer together on average, and because electrons carry the same charge and repel each other electrostatically, being closer together costs energy. If their spins are instead parallel, the Pauli principle forbids them from occupying the same quantum state, which means their spatial wave functions must be antisymmetric, which means they tend to avoid each other spatially, which means their average separation is larger, which means their electrostatic repulsion energy is lower. Lower energy is preferred. So in the specific electronic geometry of iron, cobalt, and nickel, parallel spin alignment is the energetically favored configuration. The exchange interaction is not magnetic in origin. It is electrostatic plus quantum. It is the Coulomb repulsion between electrons being filtered through the Pauli exclusion principle's constraints on which spatial configurations are permitted. The energy difference involved is not small. In iron, the exchange energy favoring parallel alignment is on the order of 100 to 1,000 times larger than the direct magnetic dipole-dipole interaction between adjacent electron moments. If magnetism in iron depended only on magnetic moments attracting each other, thermal fluctuations at room temperature would easily destroy the alignment. The exchange interaction is what makes the alignment survive at room temperature, and all the way up to 1043 Kelvin, which is 770 degrees Celsius, the temperature Pierre Curie identified experimentally in 1895 as the point where iron's ferromagnetism vanishes abruptly. That temperature is now called the Curie temperature in his honor, and the number 1043 Kelvin is worth holding in your mind because it reappears in a moment with a different meaning. At the Curie temperature, thermal energy per atom, quantified as Boltzmann's constant times temperature, becomes comparable in magnitude to the exchange interaction energy. The spins can no longer maintain collective alignment against the randomizing push of thermal vibration. The magnetism collapses sharply. Cool the material back below 1043 Kelvin and the exchange interaction reasserts itself, but the spins do not necessarily all align in the same direction throughout the bulk material. Instead, they form domains. A magnetic domain is a region inside a ferromagnetic material within which all the atomic magnetic moments are aligned in a common direction by the exchange interaction. The domain is the unit of alignment. Across the whole material, different domains align along different axes, and the boundaries between them, called domain walls, are thin transition zones, a few hundred atoms wide, where the spin direction rotates smoothly from one domain's orientation to the next. In a demagnetized piece of iron, the domains are arranged so that their fields cancel across the bulk. Some point north, some south, some east, some west, and the net external field is near zero. This is why a nail is not spontaneously magnetic, even though its individual iron atoms are participating in exchange interactions every moment. The domain structure accomplishes the same cancellation that electron pairing accomplishes in non-magnetic materials, but at a larger scale and by a different mechanism. When you bring an external magnetic field close to that nail, the domains that happen to be oriented roughly parallel to the external field grow at the expense of the misaligned domains, because it costs less energy to expand a favorably aligned domain than to nucleate a new one. Domain walls move. The favorably aligned regions enlarge. If the field is strong enough, all the domains merge into a single domain spanning the entire sample, all spins pointing the same direction, and the nail becomes a magnet. If the material is magnetically hard, meaning domain wall motion requires significant energy, the aligned configuration persists after the external field is removed because the walls cannot move back easily. This is what a permanent magnet is. A ferromagnet whose domain structure has been locked into near uniform alignment by a sufficiently strong applied field, with the lock held in place by the exchange interaction and by structural obstacles to domain wall motion, such as grain boundaries and lattice defects. The magnet you held at the start has that structure. Every atom in it is participating in exchange interactions that are entirely quantum mechanical in origin. You felt the collective output of approximately 10 to the 23rd such interactions pressing against your fingers. Now 1043 Kelvin reappears. That number is not just a limit where magnetism disappears. It is also a quantitative measure of the exchange interaction strength because the Curie temperature is directly proportional to the exchange energy per atom via a well-established mean field relationship. The exchange energy in iron works out to be approximately 0.1 electron volts per atom per nearest neighbor pair. Thermal energy at room temperature is approximately 0.025 electron volts. Iron's exchange interaction is therefore roughly 4 times the room temperature thermal energy, which is why it wins. In cobalt, the Curie temperature is 1388 Kelvin. In nickel, it is 627 Kelvin. Gadolinium, a rare earth element, is ferromagnetic only below 292 Kelvin, which is just below room temperature, which is why gadolinium is not a useful permanent magnet at standard conditions, even though its atomic magnetic moment per atom is actually larger than iron's. The exchange interaction in gadolinium simply cannot maintain alignment against room temperature thermal fluctuations. The magnitude of the exchange interaction, not the size of the atomic moment, determines whether ferromagnetism survives into the temperature range where we live. There is an equivalence worth pausing on here. The pharmaceutical industry sells compounds called iron supplements, processed, refined, dosed, delivered in capsules, and marketed for their iron content. The exchange interaction in those iron atoms, the quantum mechanical alignment tendency between their 3D electrons, is identical in character to the exchange interaction in the iron in your magnet. The chemistry of the molecule iron is bound to changes the electronic environment and disrupts the domain structure, so supplement iron is not ferromagnetic. But the underlying quantum mechanical property of the iron atom, its unpaired 3D electrons participating in exchange interactions, is not something extracted from one ion and placed into another. It is a property of the iron atom as such, present in every iron atom in the universe, in your blood, in the magnet, in the core of the Earth, in the stellar cores where the iron was first synthesized in a supernova. You purchased nothing extra. The quantum mechanics came with the atom. Now the script requires an honest calibration of where the evidence stands on several of the mechanisms named here. The existence of electron spin and its two-valued character is among the most strongly evidenced facts in physics. It is confirmed to extraordinary precision by quantum electrodynamic calculations of the electron's magnetic moment, which agree with experiment to better than 1 part in a trillion, the most precise agreement between theory and experiment in all of science. The Pauli exclusion principle is similarly uncontested. The existence of magnetic domains has been directly imaged using techniques including Lorentz transmission electron microscopy and magneto-optical Kerr effect imaging, and domain wall motion under applied fields has been filmed in real time. The Curie temperature transition in iron at 1043 Kelvin is a reproducible experimental measurement. The exchange interaction as the energetically dominant mechanism in ferromagnetism is strongly supported by both theoretical calculation from first principles using density functional theory and by experimental measurements of spin wave spectra and neutron scattering in iron, cobalt, and nickel. The specific numerical claim that the exchange energy is roughly 1,000 times the dipole interaction in iron is well established in the literature, consistent across multiple independent calculations. Where the picture is less complete, the microscopic details of domain wall pinning to specific lattice defects remain an active area of material science research, where quantitative prediction in real industrial alloys is not fully achieved. The quantitative prediction of Curie temperatures from first principles for complex alloys, rather than for pure elements, remains a computationally demanding open problem. And the deeper interpretive question of what electron spin actually is, at the level of the ontology of the wave function, is not experimentally resolved and may be a question physics cannot answer in its current form. The mechanisms described here that fall in the strongly evidenced category: electron spin, pairing, exchange interaction, domain formation. The one that sits on a more speculative shelf. Whether a fully satisfying physical picture of what spin is, not just what it does, will ever be available within any version of quantum mechanics currently under development. Beyond the basic ferromagnets, the exchange interaction organizes magnetic matter into a richer taxonomy. Antiferromagnets, like manganese oxide and chromium, have an exchange interaction that favors anti-parallel alignment between neighbors, producing a pattern where adjacent atomic spins point alternately up and down throughout the lattice. The net bulk magnetization is zero because every upspin is locally cancelled by a neighboring downspin, but the quantum mechanical order is there, fully present, measurable by neutron scattering, which was itself developed in part to probe exactly this kind of magnetic structure, work for which Clifford Shull and Bertram Brockhaus shared the Nobel Prize in Physics in 1994. Ferrimagnets, like magnetite, the naturally occurring mineral that gives lodestone its magnetism and gave humanity its first magnetic compass material, have two magnetic sublattices where the anti-parallel aligned moments are unequal in magnitude, so cancellation is incomplete and a net magnetization remains. Magnetite was the first material humans used to navigate by the Earth's magnetic field. Chinese texts describing its use as a compass date from at least the 1st century of the Common Era. Humans were practically exploiting a quantum mechanical phenomenon for more than 1,000 years before the quantum mechanics that underlies it was developed. The Chinese navigators did not need to know about the exchange interaction to sail by lodestone, but the exchange interaction was doing the work regardless. Stranger phases of magnetic order also exist and are subjects of current research. Spin glasses are materials in which the exchange interactions between magnetic atoms are frustrated by disorder. Some pairs of atoms want parallel alignment and others want anti-parallel alignment, and the geometry of the lattice makes it impossible to satisfy all these preferences simultaneously. The result is a frozen, disordered magnetic state with no net magnetization and no periodic spin arrangement, a kind of magnetic amorphousness that is still not fully theoretically understood. Spin liquids are materials in which magnetic moments remain fluctuating and disordered even at temperatures approaching absolute zero, never freezing into any ordered state, a result that violates the naive expectation that lower temperature should produce more order, and that arises from geometric frustration in the exchange interaction on certain lattice structures. Topological magnetic textures called skymions, which are stable vortex-like arrangements of spin that can only be destroyed by a process mathematically equivalent to cutting the material, have been observed in several thin film systems and are being studied as candidates for information storage because their topological stability makes them resistant to thermal disruption at very small scales. All of these are the exchange interaction, the Pauli exclusion principle, and electron spin, expressing themselves in geometries more complex than the simple ferromagnet, and all of them are active research areas with open theoretical questions. Modern technology is built on domain-scale control of the exchange interaction. Your phone contains a lithium-ion battery whose charging circuitry uses inductors wound around ferromagnetic cores, motor-driven haptic feedback using rare earth permanent magnets, speaker drivers that convert electrical current into mechanical motion via Lorentz forces on a wire in a permanent magnetic field, and an array of sensors including a magnetometer that reads the Earth's magnetic field by measuring Hall voltages induced by domain alignment in thin ferromagnetic films, all operating simultaneously in a device smaller than your hand. Hard disk drives, now coexisting with solid-state storage, wrote and read data by aligning and detecting individual magnetic domains using write heads whose gap widths were controlled to fractions of a micrometer in order to address domains small enough that a single square inch of platter surface could hold tens of billions of them. The exchange interaction energy in each of those domains had to be strong enough to hold the written state against thermal fluctuations for years, but weak enough that the write head's field could flip it reliably. That engineering problem is essentially an applied version of the competition between exchange energy and thermal energy characterized by the Curie temperature. MRI machines operate by applying a static magnetic field strong enough, typically 1.5 to 7 Tesla in clinical systems, to partially align the nuclear magnetic moments of hydrogen atoms in the water of your body's tissues, not through exchange interactions, but through direct magnetic torque on the nuclear spins. The exchange interaction is not relevant to MRI operation, but electron spin and the quantum mechanical two-valued nature of spin absolutely are, since NMR, nuclear magnetic resonance, the physical basis of MRI, was developed on the same conceptual foundation as the understanding of electron spin and obeys the same quantum rules for discrete spin states. The 1043 Kelvin Curie temperature of iron matters for MRI indirectly because the permanent magnets used in lower field MRI systems and in the gradient coil assemblies in all systems rely on rare earth permanent magnets like neodymium iron boron, whose large magnetization arises from the same exchange interaction acting on the 3d and 4f electrons of the constituent atoms, and whose Curie temperature must be well above the maximum operating temperature of the magnet assembly to ensure the permanent magnetization is stable. Electric motors convert electrical energy to mechanical work through the force a magnetic field exerts on a current-carrying conductor, a relationship described by the Lorentz force law. In motors using permanent magnets, the field comes from exchange interaction-maintained domain alignment in the stator or rotor magnets. In induction motors and transformers, the relevant magnetic property is the permeability of the ferromagnetic core material, which is how easily the domain structure responds to an applied field, a property that again derives directly from domain wall mobility and exchange interaction strength. The global electrical grid, which transmits power at high voltages to reduce resistive losses and then steps it down at distribution transformers before delivery to buildings, depends operationally on transformer cores with precisely engineered magnetic properties that would not exist without the exchange interaction. None of this is an application of an unusual or exotic physical effect. It is all the same mechanism: electron spin, Pauli exclusion, exchange interaction, domain alignment. The entire electromagnetic mechanical infrastructure of industrial civilization runs on a quantum effect with no classical explanation. And the theorem proved by van Leeuwen in 1919 remains true. In a classical universe, all of it is impossible. The motors stop, the hard drives cannot write, the transformers fail, the compasses point nowhere. The lodestone is just a rock. Go back now to that gap between the magnet and the metal surface, that pressure you felt in your fingers when you held them apart. You can identify what that is now with more precision than before. It is the macroscopic expression of a quantum mechanical energy difference between parallel and antiparallel electron spin states in the 3D orbitals of iron atoms, propagated through a crystal lattice by the exchange interaction, organized at the mesoscale into domains whose boundaries have moved in response to the external field of your magnet, and transmitted to your fingertips as force via the spatial gradient of the combined magnetic field. Every part of that description is quantum mechanical. None of it can be derived from Newton. None of it can be derived from Maxwell's equations alone. The force is real, and it requires the universe to be quantum mechanical to exist. You held the evidence in your hands.